Everybody. The first speaker is Eleana Karkani, and she is from the National and the Kapodistrian University of Athens, Greece. And the title of her presentation is Tracking Coastal Evolution Through Coastal Landforms, Longer-Term versus Short-Term Changes, Example from Greece. So I just would like to remember to switch off your microphone during the presentation, and you can ask your question at the end of the presentation by writing in the chat or asking by turn on your microphone. So please, Eleana, take the floor.
Hello, good morning, everybody. I hope you can hear me and see my screen.
Yes.
Okay,
yes.
Great, perfect. So, well, first of all, I would like to thank the organizing committee of the workshop for the invitation. I'm very happy to be with you today to celebrate not only the International Week of Geomorphology, but also the International Day of Women. And I hope that through this event, we will encourage and support more young girls and scientists to get involved with geomorphology. So, in my presentation, I will focus on two characteristic case studies from the Aegean Sea, and I will discuss relative sea level changes and coastal evolution based on data we have collected from the coastal and shallow submarine environment. Okay. So my two case studies are both located in the Aegean Sea, and the first case study, as you may have a look at the map, is located in the central Cyclades, just in the center of the Aegean. As you can also see in the map, which depicts the seismicity of the Greek region for the since 550 BC, you can see that the central Aegean is generally characterized by a relatively weak tectonic activity and the general absence of large earthquakes. So most Cycladic islands are considered to be affected by gradual subsidence, which is attributed to the crustal thinning of in the area in an extensional tectonic regime. The study area we will discuss here are Paros and Naxos Island, which are highlighted with the red square, and they are located just in the central Cyclades. So this case study is a compilation of researches that our research team has undertaken during the last years, investigating relative sea level changes and coastal evolution on these two islands. So we have studied beach rocks that have been found to about 6 meters below the present sea level in Paros and Naxos Island, and these data were combined with sediment corings, tidal notches, and also archaeological data in order to assess the relative sea level changes in the area. And all these data are afterwards compared with predictions from two glacial isostatic adjustment models in order to attempt to evaluate the tectonic component. Just a short introduction to the beach rocks. They are considered as geomorphological depositional sea level indicators. They are basically littoral deposits which are composed of beach material, and they are lithified very quickly near the sea level, and they have the capability to record the position of the corresponding shoreline. And the cementing agent of the beach material is most commonly high magnesium calcite or aragonite, and beach rocks have been frequently used as sea level markers, especially in the Mediterranean region, so I think they are relatively well known to most researchers. And although their accuracy as sea level indicators has been debated in the literature, there are some key elements that allow us to determine the genetic environment of the beach rocks and therefore their formation zone. So the examination of the cement characteristics and the microstratigraphy can allow us to identify the type of cement and therefore the spatial relationship between the past shoreline and the beach rock formation zone. So in the study area, in Paros and Naxos Islands, we have investigated 9 beach rock sites. You can see to the map on the left, the studied sites. Most of the sites are located on Naxos Island, and a few others are also on Paros Island. And in fact, the western coasts of Naxos are characterized by the presence of multiple extensive submerged beach rock slabs, and you can see this characteristically in the two photos in the middle of the slide. In order to collect data for the study of the beach rocks, we did a detailed spatial mapping of submerged beach rock slabs. In order to define their spatial extent, we performed an aerial survey with an unmanned aerial vehicle in selected sites. At each of the studied sites, we did one or more underwater transects in order to measure the width of the beach rock slabs and their depth in relation to the mean sea level. And where possible, we tried to also identify the sediment bedding. And we also sampled from the front and the end of each beach rock slab. The samples were used to prepare thin sections in order to examine the cement. So the thin sections were examined using a polarizing microscope for petrographic and microstratigraphic analysis. And these observations allowed us to characterize the constituents, the presence of bioclasts, and also the type of the cements. The samples were also dated with luminescence dating. 7 beach rock samples were dated by using optically stimulated luminescence dating of feldspar and also infrared stimulated luminescence dating of feldspar. So in order to use the beach rocks as sea level index points, we followed the protocol as proposed by Maus and her colleagues in 2015, and we only converted to index points those samples that showed clear intertidal formation. So all the samples that we dated showed clear intertidal formation based on their cement. And for this reason, we considered an indicative range between the mean high tide and the mean low tide for the beach rock samples. Here you can see a characteristic aerial view of the submerged beach rock slabs from Naxos Island. This configuration is very characteristic along the entire western coast of Naxos. And on average, in the study area, we have found 3 or even 4 slabs at each site, and the maximum depth identified was at about 6.3 meters below sea level. So before I discuss about the relative sea level changes, there are the beach rock submarine configuration allowed us also to have insights into the paleogeography of the coastal zone. So there are 2 sites on the western coast of Naxos that are very representative and appear to have recorded very well the morphological configuration of the coastline in the last 4,000 years or so. The first of these sites is Plaka. You can see here on the map, it is on the western part of Naxos Island. And at this site, we can see that the submarine beach rocks can be followed parallel to the modern coastline for more than almost 2.5 kilometers. And we can identify 3 paleo shorelines. You may note that even most of them are very similar to the geometric shape of the modern coastline. However, if we have a look at the northern part of the coast, let me use also my laser pointer. If we have a look at this part of the coast of Plaka, we will see that the shoreline morphology recorded by the beach rocks appears rather different. The orientation of the paleo shoreline is not parallel to the modern coastline, but appears to end up to a shallow outcrop of granodiorite, which is highlighted by the red circle here. And this morphological configuration may indicate that the geomorphology of the coastal zone in this area was different, with the possible presence of a paleotombolo and perhaps the existence of 2 bays due to the presence of this granodioritic outcrop. This morphological configuration is probably dated at about 4,000 years before present. Another interesting example of coastal evolution, we also find that the western coast of Naxos at Agios Georgios. The site is a little further to the north of the previous site, as you can also see in the map in the bottom right corner. Here, the submerged beach rocks have been distinguished in three shorelines, and the second one has been dated at about 104,000 years ago. And we can see that the present configuration of the submerged beach rocks suggests that the paleo shorelines in this area were more extensive and probably reaching the two edges of this bay, of Agios Georgios Bay. And the beach rock slabs extending almost parallel to the coastline also reveal the continuous shoreline recession in this bay. As I noted in the beginning, we also used sediment corings to assess the relative sea level changes in the area. Our research team has performed a series of corings in both islands in coastal lagoonal environments, and we used multipropsy analysis for the core analysis with sedimentology, paleontology, and radiocarbon dating. So we used the sediment corings to deduce relative sea level index points. And following recent published protocols, we attributed an indicative range of from 0 to -2 meters for the samples found in an open or marine influenced lagoon, and an indicative range from 0 to -1 meter for inner or semi-enclosed lagoons. And for samples that were found in a brackish environment, we considered that they were most likely deposited within 50 centimeters from the former mean sea level. And last but not least, another coastal landform that provides evidence for relative sea level changes in our study area are also tidal notches. Tidal notches are the undercuttings a few centimeters to several meters deep, and they are cut in steep calcareous cliffs at or near sea level. And the profile of a tidal notch is considered as an excellent sea level indicator because it provides information about the duration in which the mean sea level remained at the level of the notch vertex. You can see the notch vertex here in the bottom figure. And we can also have information if the notch is immersed or submerged on the speed of the emergence or submergence. So in the study area, past researches through underwater geomorphological survey by Evelpido and her colleagues in 2014 revealed that there is widespread evidence of multiple submerged tidal notches, and they identified at least 7 former shorelines between 280 centimeters and 30 centimeters below the present sea level. And the researchers, by combining the morphology of the submerged notches, the seismicity, history of the area, and by correlating their findings with archaeological information, they concluded that rapid subsidence events took place in the area, probably of seismic origin. And as we may see on the sketch on the bottom here, these relative sea level changes have been relatively dated that have taken place after 3,300 BP. So by using all this information, we end up with this summary plot for the relative sea level changes in our study area. The plot has derived from the corings, from Paros and Naxos Islands, from the study of the beach rocks, and by taking into consideration also 2 archaeological estimations of relative sea level. So what we may note is that our data support the relative sea level that rose by 2 meters in the last 2,000 years and by at least 3.9 meters since 4,500 years BP. You may note that the circled data were rejected as they provided ages that were inconsistent with the chronostratigraphy of the course. And in order to interpret the observational relative sea level data, we also considered predictions from 2 glacial isostatic adjustment models. And in comparison with the modeled curves, we can see that our points have a lower position. So we calculated average rates of tectonic subsidence for 3 different time frames, as you can also see in the slide, this calculation was based on the mismatch between the models and the observations for the study area. So considering the difference in elevation between the sea level estimates from our data and each of the models employed. So in summary, since 5,500 BP, we found comparable tectonic subsidence rates of about 1 millimeter per year. And the average rate of the tectonic subsidence does not appear constant. It seems lower for the time span between 2,500 and 5,000 years BP, being close to 0.7 millimeters per year. And it appears higher since 2,500 BP, suggesting that the subsidence rates in the central Cyclades and Paros and Naxos Islands in particular have not been constant since for the time period considered. So this subsidence trend in the central Cyclades is most likely a combination of seismic events, as also suggested by the tidal notches, and of gradual long-term subsidence due to the dominance of an extensional structural pattern. We move to the second case study. We now go to the Mid-Eastern Aegean Sea. The second case study is Samos Island, and this site has a more complicated sea level history in comparison to the Cycladic region. So Samos is located in the Mid-Eastern Aegean Sea. It is less than 1.5 kilometers from the West Anatolian coasts, and the broader Samos region is situated in an interaction area between the Aegean microplate, the subducting African plate, and the Anatolian microplate. So a few months ago, on the 30th of October of 2020, an earthquake of a magnitude of 7 took place just on the north part of Samos. You may note the location of the earthquake by the red star on the map. It caused extensive damage not only on Samos but also on the opposite side, on the near coasts of Turkey. And here on the map you can see the main tectonic features in and around the island of Samos. And after the earthquake, also a tsunami was also triggered after the event. So the island is characterized by a complex tectonic history. Their evidence have been found of late Holocene uplift as a result of past earthquakes, mainly from the northwestern coast of the island, as we can see on the map on the top here. While on the other hand, if we look at the southeast coast, subsidence has been noted based on the presence of submerged geomorphological and archaeological indicators. So our research group, this research that I show you in these slides, aimed to re-examine the various sea level indicators in Samos Island by comparing past with new measurements in order to understand and quantify the ecoseismic movements that were caused by the recent seismic event of October 2020, and try to shed light on the tectonic regime of the island. So our team did extensive fieldwork in the past, in April 2015, and also in November 2020 along the coastal zone of Samos, both on the coast and the underwater part. The underwater survey was accomplished by snorkeling and also free diving, and we used a boat in order to be able to access all sites. The sites that were examined in 2015 were revisited and remapped in early November of 2020, and we also mapped additional. I don't know what happened.
We are not seeing your screen.
I know, I don't know what happened. I will try again. I'm not sure what happened. Okay. Now?
It is coming.
It's coming. Yes, now
Yes.
it's okay.
Okay, sorry, I don't know what happened. It looks like I lost the connection. Okay, so as I was saying, we examined the sites in 2015 And we visited the same sites in November 2020, and we also visited additional sites around the island in order to document possible vertical changes after the earthquake of 2020. And sites with evidence of former uplift reported by past research were also measured in order to better quantify the new vertical tectonic displacements. So this is a summary slide of the results of our research. And based on our findings, the northwest part of Samos Island has been co-seismically uplifted by 20 to 35 centimeters, while if we have a look at the southeastern part of Samos, the re-examination of the SABE of the submerged tidal notches from 2015 and their examination again in November 2020 revealed that they have been uplifted, but they have remained drowned. You can see an example from the sketch on the bottom of the slide. And overall, our findings have shown that the island has been co-seismically uplifted, but with different magnitude. We found the largest uplift at the northern part of the island, so on this part of the coastal zone, with the highest values on the northwestern tip of the island. And although the southern part of Samos has experienced many submergence events in the past, it seems that during the event of October 2020, it has been uplifted by up to about 23 centimeters, while based on our findings, the uplift is fading out towards the northeast, the east and northeast of the island. So I conclude this presentation and thank you very much for your attention.
Okay, thank you, Eleana, for your presentation. And if someone has any question, please you can ask by turn on your microphone or by writing in the chat. I can see. No, there are no questions. I have one question for you, Eleana.
Yeah.
One for regarding the first case study and one for the second case study.
Okay.
In the first case, I would ask if the subsidence rate that you detected are still recognized in the recent coastal dynamics. And regarding the second case study, I was wondering if you have combined your data also with geodetic or remote sensing data, such as interferometric, radar interferometric data, in order to confirm the uplift that you detected.
Okay, I can ask first. I didn't really understand the first question, but I can answer first to you to the second question in order to.
Okay.
In our research, we didn't use any other data, but we did compare our results with the geophysically modeled displacements that were available through publications, and also through GNSS observed displacements. And our results are basically in agreement with the differential uplift that was recorded through other methods for the island. So,
okay.
I hope I answer your question.
Okay. And regarding the first case study, you show that the area is characterized by Holocene subsidence rate variable, and if in the recent dynamics this subsidence is still recognized. I was wondering, or if you have data that can confirm this subsidence rate, the present day.
From the present day, not so much. We don't have many data from the present day in terms of if you're referring to measurements from the coast. But We have a lot of, both in Paros and Naxos Islands, we have many archaeological remains that are submerged to various depths. So we can find, for example, in Paros, a Roman building that is just near the sea level, but it is below the sea level. It's about 50 centimeters, let's say, below the sea level. So in general, even there are evidence that show us the subsidence, but the point was to also be able to calculate, to speak with numbers.
Yeah.
So I hope I covered your question more or less.
Excuse me, there is also one question in the chat from a colleague, Lorraine.
Yes.
Yeah.
The question is, what is your theory for the reason behind the change in the rate of subsidence in the Aegean?
Okay. Well, okay. Just it's not about the Aegean. It's about the central Cyclades, because the Aegean has a very complex tectonic situation. But we think that this change in the subsidence has to do with probably recent seismic events that have affected the subsidence rate. So it seems that recently we've had some tectonic events that have caused also abrupt changes that were superimposed on the gradual subsidence that is taking place in the central Cyclades.
And there is also another question. Did you are planning to cross-reference these results with archaeological indicators?
Oh, nice question. We have also worked with archaeological data. I mean, the time was a bit. I tried to focus on our main findings, but we have also published data related to the archaeological indicators in the study area. So we have already done also this work. I can give you the link if you're interested to have a look in the chat.
Yeah, it would be nice.
I will do that.
The question was from Judith Gatt, and she also congratulated for the presentation.
Thank you very much.